across your hand.
What would happen if you threw a boomerang on the moon? It's a fascinating question that quickly spirals into an exploration of physics, atmosphere, and motion. On Earth, a boomerang should come back. But the moon is a different world, where familiar rules no longer apply. It's a silent, airless realm governed by a gentle gravitational pull. Would it simply sail off into the dusty void? It forces us to strip away our earthly assumptions and look at the fundamental forces at play. The lunar surface is a near-perfect vacuum where there is no atmosphere. The moon's gravity is only about 1/6 as strong as Earth's. An object launched on the moon will travel much farther, no air and much weaker gravity. To truly understand this, we need a plan. We'll break down the problem piece by piece, examining every detail. First, let's establish a baseline by understanding how boomerangs work on Earth. It's physics, not magic. The V-shape acts like airplane wings, creating lift as it spins. Understanding this is key. Next, we'll consider the moon's environment, no atmosphere and reduced gravity. This affects how objects move, a concept demonstrated by Apollo 15. Now imagine throwing a boomerang on the moon. How would it fly without air? Would it curve or fly straight? It's more complex than a simple answer. What if we designed a lunar boomerang? This question illuminates broader physics principles. Let's begin our investigation here on Earth. To understand why a boomerang wouldn't return on the moon, we need to know why it does on Earth. The secret is aerodynamic forces. Each arm is essentially a wing, like an airplane wing. As it spins, the shape forces air over the top to travel faster, creating lower pressure. This generates lift. A boomerang is thrown vertically, spinning like helicopter blades. The top wing moves with the throw, while the bottom moves against it. The faster wing generates more lift, creating an imbalance that initiates a turn. This steers the boomerang into a curve. Without air, there's no airflow, no lift. The curved flight is a consequence of its design interacting with Earth's atmosphere. The second piece of the puzzle is a fascinating physical phenomenon known as gyroscopic precession. This might sound complicated, but we see it in action all the time with spinning tops or bicycle wheels. In simple terms, when you have a spinning object, like our boomerang, and you try to apply a force to tilt it, the object doesn't tilt in the direction you push. Instead, it tilts at a point 90 degrees ahead in the direction of the spin. This strange, counterintuitive behavior is the key that translates the uneven lift we just discussed into a smooth, circular flight path, rather than a clumsy tumble through the air. Let's apply this to our boomerang. As we established, the top wing is generating more lift than the bottom wing. This creates a force that is trying to push the top of the boomerang up and over, but because the boomerang is spinning, gyroscopic precession takes over. The force applied at the top of the spin doesn't cause the boomerang to flip over backward. Instead, the effect of that force is felt 90 degrees forward in the direction of rotation. This means the leading edge of the boomerang is the part that actually tilts, causing the entire spinning disc to bank into a turn, just like a motorcycle leaning into a corner. This gyroscopic effect is what maintains the boomerang's stability and orientation throughout its flight. It's a constant self-correcting mechanism. The aerodynamic force of unequal lift continuously tries to tip the boomerang over, and gyroscopic precession continuously translates that tipping force into a steady banking turn. The two phenomena are locked in a delicate dance. Without the spin, the unequal lift would just cause the boomerang to flutter uselessly to the ground. Without the unequal lift from the air, the spin alone would do nothing to alter its path. Both are required for the magic to happen, and both are intrinsically linked. On the moon, a spinning boomerang would still possess gyroscopic properties. If an astronaut in a pressurized lunar habitat could somehow apply a force to the top of a spinning boomerang, it would indeed precess and tilt 90 degrees forward. However, in the lunar vacuum, there is no air to create the necessary aerodynamic force in the first place. There's no unequal lift trying to tip it over. Therefore, there is no force for gyroscopic precession to act upon. The spin would provide stability, preventing it from tumbling, but it would have no influence on its trajectory. It would fly straight, a stable but uncurving projectile. The thrower's skill marries human action with physical principles. They must impart forward velocity and a high rate of spin. The angle of release is also critically important. It must be thrown with a specific vertical tilt. Furthermore, the thrower must account for the wind. They throw across the wind, allowing it to assist the boomerang's return. On the moon, the air would be missing, making the thrower's technique irrelevant. Let's travel to the moon, where the most profound difference is the near-total lack of atmosphere. On Earth, air is the partner that lets boomerangs return. On the moon, there's no air, no wind, no medium for flight. In this vacuum, there's no lift, no drag, and no aerodynamic magic, just inertia and gravity. The boomerang's carefully crafted wings are useless. It's now just a spinning projectile. Once thrown, it follows a simple, uncurving path, no return, no dance, just a silent arc. The absence of air erases all hope of a boomerang's return flight. Gravity on the moon is only 1/6 of Earth's, making everything lighter and every throw go farther. A boomerang tossed here would soar in a long, slow arc, traveling much farther than on Earth. The weak gravity means a gentle, extended flight, but it doesn't make the boomerang turn. Gravity pulls objects down, not sideways. So the boomerang's path is a simple, stretched parabola. The absence of aerodynamic lift means no return. The boomerang just keeps going until it lands. On the moon, every throw is a one-way trip. The only question is how far it will go before it touches down. The moon's environment is brutal: scorching heat and sunlight, freezing cold and shadow. Traditional wooden boomerangs would crack or warp. Even modern materials are tested by these extremes. Solar radiation and micrometeoroids constantly bombard the surface, slowly degrading anything left exposed. The lunar surface is a harsh alien world, far more than just a vacuum. While these factors don't change the boomerang's flight path, they challenge its very survival. On the moon, even the boomerang itself is at risk before it's ever thrown. Picture an astronaut on the moon, boomerang in hand, ready to throw. The launch is silent, no whoosh, no sound, just a motion in the void. The boomerang spins and flies forward, but in the vacuum the spin does nothing to curve its path. Its wings slice through emptiness, as useless as fins on a fish out of water. The boomerang becomes a simple projectile, its fate sealed at release. It glides away in a straight line, smooth and silent, never to return. The moon's physics make the boomerang's journey a one-way show. The boomerang's flight on the moon is a perfect parabola pushed by the throw, pulled gently down by gravity. It soars higher and farther than on Earth, tracing a long, graceful arc. There's no sideways curve, no return, just a majestic one-way trip. The astronaut watches as the boomerang sails away, a live demonstration of pure Newtonian motion. No drag, no lift, just inertia and gravity at work. The boomerang's journey is a testament to the simplicity and beauty of physics in a vacuum. On the moon, the boomerang's spin doesn't steer, it stabilizes. Like a spinning top, the rotation keeps the boomerang from tumbling, ensuring a smooth, steady flight. With no air to disrupt it, the boomerang maintains its orientation perfectly. The spin makes the flight visually impressive, but it can't bring the boomerang back. The astronaut's skillful throw ensures a stable, spinning arc. Nothing more. On Earth, spin is the heart of the return. On the moon, it's just for show. The boomerang's one-way flight is smooth, stable, and utterly unreturning. Every object thrown on a planet or moon will eventually reach the highest point of its trajectory, an apex, before beginning its descent. For our lunar boomerang, this moment would occur after a surprisingly long time and at a considerable altitude. As it flies away from the astronaut, its upward velocity is slowly being chipped away by the moon's gentle gravity. Eventually, the upward motion stops entirely for a fleeting instant. At this peak, the boomerang hangs, suspended against the black sky, with the Earth perhaps visible as a beautiful blue marble in the distance. This is the turning point of its vertical journey. From this apex, the boomerang begins its long, slow fall back toward the lunar surface. The descent is a mirror image of the ascent. Gravity, which was slowing the boomerang down on its way up, now begins to accelerate it downward. It starts to pick up speed, but because the gravitational pull is so weak, the acceleration is gradual. The descent is just as slow and graceful as the climb. The boomerang would appear to float down, taking its time to return to the ground. All the while, it continues to travel forward, completing the second half of its wide parabolic arc. During this entire phase, the climb, the apex, and the descent, the boomerang has not turned back toward the thrower by even a single inch. Its forward motion continues unabated, indifferent to its vertical travel. The astronaut is now watching the boomerang getting smaller and smaller in the distance as it completes its flight far away from where it started. The hope of a return, which vanished the moment the boomerang was released into the vacuum, is now visually confirmed. The object is behaving exactly as physics predicts, like a simple cannonball, not a magical returning stick. The total flight time would be remarkable. A boomerang throw on Earth might last for 10 to 15 seconds. On the moon, with the same initial velocity, the boomerang could remain airborne for a minute or more. This extended duration would give the astronaut plenty of time to contemplate the forces at play. They would witness a perfect, real-world demonstration of projectile motion in a low-gravity, airless environment. The long, lazy descent would be the final, elegant chapter in a story of a one-way journey, a flight path dictated by gravity and inertia alone. After its long and graceful flight, the Boomerang's journey must come to an end. As it descends, it finally meets the lunar surface hundreds of yards away from the astronaut. The impact, like the launch, would be completely silent. There would be no thud, no clatter of wood or plastic against rock. Instead, the boomerang would simply strike the ground, its kinetic energy absorbed by the soft, powdery lunar regolith. The only visual evidence of the impact would be a small, beautiful spray of dust, ejected outwards in sharp, perfect rays unhindered by air resistance before falling straight back down. The boomerang would likely come to rest right where it lands, with very little bouncing or skidding. The loose, fine-grained nature of the lunar soil is excellent at absorbing impacts. Furthermore, the object's stable, spinning motion would likely cause it to land flat, settling into the gray dust. There it would lie, a strange terrestrial artifact on an alien world, a testament to a failed experiment in aerodynamics. It would be a lonely marker, hundreds of yards from its owner with no way to get back on its own. The astronaut would need a long walk, or perhaps a ride on the lunar rover to retrieve it. This final resting place marks the definitive conclusion of our experiment. The boomerang was thrown, and it did not come back. It flew far, it flew gracefully, but it flew in a straight, predictable parabolic arc. Every step of its journey, from the silent release to the dusty impact, was governed by the fundamental physics of a vacuum and low gravity. The complex interplay of forces that allows a boomerang to perform its circular dance on Earth was completely absent, and the result was an object behaving just like any other thrown rock, albeit a very stylish and well-spun one. The boomerang now becomes part of the lunar landscape, at least temporarily. It might be coated in a fine layer of the electrostatically charged dust. It would sit in the harsh environment, exposed to extreme temperatures and unfiltered radiation. This dusty, silent end is the ultimate answer to our question. What happens when you throw a boomerang on the moon? It flies beautifully, it travels far, and then it lands, staying exactly where it falls. A silent monument to the unyielding and universal laws of physics that change so dramatically from one world to the next. This conclusion naturally leads to a fascinating follow-up question. If a terrestrial boomerang doesn't work, could we design a moonerang that would? Could human ingenuity devise an object that could be thrown and would return to the astronaut on the moon? Since aerodynamics are useless, we would have to abandon the familiar V-shape and airfoil design entirely. We would need to rely on a different set of physical principles to generate a turning force. The most obvious candidate would be some form of propulsion. We would have to build a boomerang that steers itself. Imagine a boomerang-shaped device equipped with tiny, precision-controlled rocket thrusters or jets of compressed gas. An onboard computer complete with accelerometers and gyroscopes could calculate the object's trajectory. After being thrown, the system would activate. At a predetermined point in its flight, small thrusters on one side would fire in carefully timed pulses. These bursts of propulsion would provide the necessary sideways force to push the boomerang into a wide, curving path, steering it back toward the thrower. It would be less of a boomerang and more of a smart, semi-autonomous drone. The design challenges would be immense. The device would need to be lightweight, yet robust enough to house a power source, a computer, sensors, and a propulsion system. The navigation would need to be incredibly precise to guide the object back to a specific point, the astronaut, over a large distance. It would have to account for the initial velocity of the throw and the moon's gravity to calculate the perfect return arc. The astronaut might even wear a beacon that the moonerang could home in on, making the return more accurate. This would be a remarkable piece of engineering. Ultimately, while such a device is theoretically possible, it highlights the fundamental difference between the two scenarios. The genius of a traditional boomerang is its simplicity. It's a passive object that cleverly harnesses the natural forces of its environment, the air, to perform its trick. Our high-tech moonerang, on the other hand, would be an active, complex machine. It would have to carry its own forces with it in the form of propellant. Its return would be a triumph of raw technology, not elegant physics. It proves that on the moon without an atmosphere there is no free lunch. To make something turn, you have to actively push it. Could our astronaut use the lunar landscape to make the boomerang return? Imagine throwing the boomerang at a precise angle so it travels across the crater floor and bounces back. The surface of the crater wall is key. A hard surface is essential for an efficient transfer of energy. The spin is important for how the boomerang interacts with the surface upon impact, like a billiard ball. The astronaut would have to calculate the perfect angle of incidence and account for the boomerang's long flight path. It would be a breathtaking sight, a trick shot on a planetary scale that relies on precision and calculation. This highlights using the environment to your advantage. A successful return achieved by playing a game of pool with the lunar landscape itself. Let's imagine two astronauts on the moon, a significant distance apart. The boomerang, failing to return, becomes the basis for an ultimate game of long-distance catch. Because of weak gravity and no air resistance, astronauts could throw the boomerang vast distances with ease. The spin would make its flight path smooth and predictable, arriving without chaotic fluttering. The astronauts could practice throwing it back and forth, a silent, graceful exchange on a scale barely comprehensible. Unburdened by Earth's gravity, they could leap with agility to make spectacular catches. However, they would contend with bulky suits restricting movement. This reframes the boomerang's purpose. From a solitary tool on Earth to an object for connection on the moon, its failure to return becomes its greatest asset, defined entirely by its environment. Our cosmic journey to answer a simple question: what happens if you throw a boomerang on the moon? It does not come back. It sails through the vacuum, its path dictated by the throw and the moon's gravity. This illustrates the differences between worlds. Earthly intuition isn't a universal truth. The boomerang's return on Earth is due to our atmosphere. It's a lesson in physics, cosmic in scale. Asking what if opens new avenues of thought. Our boomerang on the moon is a symbol of curiosity. It represents the bridge between Earth and our future in the cosmos. Even simple questions can enrich our understanding of the universe.